Hi there, this is Coach Eikrem, and welcome to video number 2 on our mole unit. Where we left off in the last video, we had just introduced the concept of molar mass, and we talked about how they came up with that concept and why we use it. And so now what we're going to do is we're going to apply that. So the first concept that's really important that you need to understand is that 1 mole of anything on the periodic table is going to be the molar mass in grams. So this is going to be very easy for us to find. If you look at your periodic table and you go to, say, phosphorus, you look at the mass of phosphorus, it is 30.97. That is the molar mass in grams of phosphorus, and that is also 1 mole of phosphorus. So if you have 30.97 grams of phosphorus, then you have 1 mole of phosphorus. And we also know from the previous video that 1 mole of anything, when you count it, is going to be 6.02 times 10 to the 23rd. And so if you've got 30.97 grams of phosphorus, you therefore have 1 mole, and therefore you have 6.02 times 10 to the 23rd particles of phosphorus. The same would apply for aluminum. You can find the molar mass of aluminum by just looking on the periodic table because it's an element, and it's going to be 26.98 grams in 1 mole. So 1 mole of aluminum is going to be the equivalent of 26.98 grams, and it's also going to be 6.02 times 10 to the 23rd particles of aluminum. And you can also do the same for helium and silver. Now, it's important to remember when you're writing this unit, remember we talked about this at the end of the last video, when you're writing this, it's going to be, so for example, for aluminum, it would be 26.98 grams per mole, because that's what that unit is. That is how many grams are in 1 mole. That is the definition of the molar mass. So that's how you find the molar mass of an element. So if we were going to do problems using this concept, it says how many grams of silicon are in 5 moles of silicon. So this is our given. This is where we're going. And so we're going to start with 5.0 moles of silicon. And we know that to get to grams, we know that the molar mass of silicon is going to be equivalent of 1 mole. So this is essentially, our molar mass is essentially one big conversion factor that we're going to use to convert between moles and grams and vice versa, go from grams back to moles. So in this case, we know that if you want 1 mole of silicon, or if you have 1 mole of silicon, then it's always going to be the equivalent of the molar mass, which if you look on the periodic table, is going to be equal to 28.09 grams. So remember, that's where that grams per mole comes in. Okay, that's that unit right there. So then you cancel off your moles, you do the math, and remember you have to take it to 2 significant figures, so you multiply across and divide, and you get 140 grams of silicon. So we just converted. If we had said we had 5 moles of something, you want to know how many grams that is, we use the molar mass. This would be like the same equivalent of if I said I had 144 eggs, how many dozen eggs did I have? You know that 1 dozen is 12, and so you would just essentially do the dimensional analysis in your head. This is the same exact concept, except your conversion, instead of 12 eggs in 1 dozen, is your molar mass for that particular element. So if you were going to do problem number 2, you got how many moles of potassium are in 136.9 grams of potassium. So we're going to moles, 136.9 grams. Okay, and this time you're going to use the same conversion factor, but remember, you have to be able to cancel out like units. So this time moles is going to be at the top. And it should be K. There should be K there as well. And if you look on your periodic table, the molar mass of potassium is 39.10 grams of potassium. So do your math, multiply across and divide, and remember you have to take it to 4 significant figures. So originally you get 3.50128, and you're going to round that to 3.501 moles of potassium. And I should have also boxed my answer up here as well. And there we go. And again, you're just using that conversion factor, and it doesn't matter. People get very obsessed over which one goes on the top of the line or the bottom of the line. That's not what's important. Remember, this is a ratio. It is something that can be interchangeable, and you always want to make sure you can cancel off like units. So it's all well and good if we're finding the molar mass of an element. You just look on the periodic table and look it up. It's very easy, okay? But what if you have a compound? It's actually quite easy as well. I'm going to scroll down a little bit here. New feature, I'm just discovering I can do this. There we go. Fabulous. Okay. So it says finding the molar masses of compounds. So if you were to say find the molar mass of H2O, okay, in our H2O molecule, we've got 2 hydrogens, so we've got 2 times hydrogen, and we've got 1 oxygen. So in order to find the molar mass of that whole compound, essentially you're going to add up the number, the molar masses for each individual element and times it by how many times you have it. And that's easier actually done than said. So if you're looking for hydrogen, you've got 2 hydrogens. If you look on your periodic table, hydrogen's molar mass is 1.008, and you're going to times that by 2. And then oxygen's is 16.0, and you're going to times that by 1. You're going to get your answers for both of those. You're going to add them together, and you're going to end up with 18.015 grams per mole. That is your molar mass of water. So go ahead and try it with NH3. Pause the video and see if you can calculate the molar mass for NH3. All right, let's do it together to check our work. If you were calculating the molar mass of NH3, you are going to add up 1 nitrogen. So nitrogen is going to be 14. You only need 1 of them. And then 3 hydrogens, so 3 times hydrogen. Remember, it's 1.008, so 3 times 1.008. You're going to add those up, and you're going to get 17.031 grams per mole. Remember, units are very, very important in this unit. No pun intended. All right, let's look at this one. CaOH2, which is calcium hydroxide. You should be able to name that by now. If you're looking at this one has parentheses, which makes it, not trickier, but easy to mess up on if you're going quickly. So you, again, you can do this one of 2 ways. You can count up each individual element. You can say we've got 1 calcium, okay? And then remember, you've got your subscript here, so you've got 2 oxygens and 2 H's. So you can either do 2 times oxygen and 2 times H and add it all up that way. Or what I like to do is I like to find out what the molar mass of the OH piece is and then times that whole thing by 2. And then add the calcium into it. Either way is completely 100% acceptable. You just have to find the way that works well for you. But if you're doing it this way, 1 calcium is 40.08. 2 oxygens is 2 times 16.00, which is 32.00. And then 2 hydrogens is 2 times 1.008, which is 2.016. And when you add all of that up, you are going to end up with, if I can find my notes with this, did I write it down? I thought I wrote it down. Oh, I did write it down. 74.096 grams per mole. Sorry about that. There we go. And you can do this for any compound, no matter how complex, no matter how long, no matter how many elements are in there. You just take it one piece at a time, break it down, and add up the molar masses of each individual element. So if we wanted to use this conversion practice, it says how many grams of ammonia are in 25.0 moles of ammonia. So this is what I'm given. This is where I'm going. So we've got 25.0, moles of ammonia, and you should know that ammonia is NH3. Okay, so if you're solving this problem, in 25.0 moles of ammonia, you're trying to get to grams. Remember, the conversion factor for that is the molar mass of ammonia. So 1 mole of ammonia is going to be equal to how many grams the molar mass is. So you have to calculate it, add up 1 nitrogen, 3 hydrogens together, and you end up with 17.03 grams of ammonia. Moles cancel out. Multiply across, you get 140.45. You have to round to 3 significant figures. So it's 140 grams of ammonia. And that's a little bit trickier because you have to take a second in the middle and calculate this molar mass. But it's not any harder, it's just a little bit more work per problem. In this one, you've got 54.0 grams of silver nitrate, and you're going to moles. So you've got 54.0 grams. And silver nitrate is going to be AgNO3, which you should know as well. Okay, and 1 mole of silver nitrate is going to be 169.87 grams of silver nitrate. And you should get, when you round to significant figures, 0.318 moles of silver nitrate. Remember, all these are interchangeable. You notice up here we've got moles on the bottom, and down here we've got moles on the top. It's more important to remember that you're canceling out the units and you're using it as a ratio and a conversion factor to get from moles to grams. Okay, so the last conversion factor that we're going to learn is probably the simplest and the most straightforward. Avogadro discovered something very special about gases and moles. If he said, if you're at the same temperature and pressure, equal volumes of gases are going to contain equal number of moles. So we just stick to the case of standard temperature and pressure. We call this STP. It's defined as 0 Celsius and 1 atmosphere of pressure, which we'll get into more in gas laws. But the law here and the rule is that if you have STP, 1 mole of any gas will always have a volume of 22.4 liters. So what does that mean? That means you can solve problems like this. If it's asking you, if you say you've got 44.8 liters of neon and you want to know how many moles that is, you know that if you're at STP, you can solve that problem very, very easily. So if you've got 44.8 liters of neon, you don't even look up the molar mass for this problem because you're going from liters to moles, and you know that 1 liter of any gas at STP is going to be equal to 22.4 liters. So 22.4 liters of neon is going to be equal to 1 mole of neon. Cross off your units, multiply across, correct number of significant figures, and you get 2.0 moles of neon. Go ahead and see if you can do number 2 and number 3 on your own. All right, welcome back. Let's check our work, see how we did. So we've got 0.33 moles of CO2 gas, and we're going to liters. So we start with 0.33 moles of CO2, and then 1 mole of CO2. Since it's at STP, it's 22.4 liters of CO2. Remember, this doesn't apply if it's not at STP. And when you solve it out, you get 7.4 liters of CO2. And when you solve the one at the bottom, 1.25 liters of helium. Okay, 22.4 liters of helium is in 1 mole. And you end up with 0.0558 moles. I hope I didn't just do the wrong one. There we go. Okay. All right. So you've learned all the basic 1 steps that you can do. You can go from moles to molecules. You can go from moles to atoms, moles to particles. Now you know you can use molar mass to go from moles to grams and grams to moles. And you can also use STP to go from liters to moles. So now you might have to put them together, and this is going to be a mixed mole problem or a 2-step problem. And what I like to think about with this is moles is sort of the most important piece here. You're going to have, everything's going to use moles kind of as like the, kind of like an interchange on the highway. So if you're trying to get, for example, from atoms of iron to grams, we don't have a conversion factor that takes us directly from atoms to grams. Okay, we haven't learned one, but we do know how many atoms are in 1 mole. We do know that there's 6.02 times 10 to the 23rd atoms in 1 mole, and we also know that we can calculate how many, what the molar mass of iron is. So we know that 1 mole of iron is going to have, and if you look on your periodic table, it's 55.85 grams. So we can do a 2-step problem here to go from atoms to grams. So if you start with your given, which is 4.2 times 10 to the 22nd atoms of iron. Okay, we know we're first going to get to moles. Remember, moles is our middleman. So in this case, we're going to be going to moles first, and then going from moles to grams. Okay, this step is going to use Avogadro's number, and this step's going to use my molar mass. Okay, and you can go backwards. You could even start from grams, go back to moles, and then go back to atoms or particles or anything else you're looking for. And you can also go from atoms to moles and then moles to liters now. You can use any one of these interchangeably. So in this case, we've got 6.02 times 10 to the 23rd atoms of anything, remember, not just iron, atoms of anything are in 1 mole. So now we're at moles, now we're at that middleman, and now we can take that and we can go from atoms using, we came from atoms, we're going to go to grams using our molar mass. So we looked on the periodic table, we said it was 55.85, so 1 mole of iron is going to be 55.85 grams of iron. Remember, cross off my units. Always make sure, this is where dimensional analysis skills from the beginning of the year come in handy. Make sure you can cancel your units. You are going to multiply across and divide, and I'm looking for my work for this one so that I can, here it is. Okay, multiply across and divide, and you're going to get 3.9 grams of iron. It has to have 2 significant figures. That's a 3 right there. So 3.9 grams of iron. So here's another one worked out for you just so you can see it. So in this case, you're starting with 4.6 moles and you're going to formula units. Okay? And this one's actually just a one-step problem because you're given the number of moles. So remember, that's how you can kind of tell the difference. If you don't see moles in the problem, that means you probably have to use moles as the middleman to go from kind of one end of the spectrum of the other. In this case, since you have moles, then you can go directly to what you're looking for. Just kind of the rule of thumb is if you have moles, you can kind of get anywhere. If you don't have moles, get to moles, and then you can go anywhere from there. So in this case, you started at moles, used your conversion that we learned at the very beginning, and then you get your answer. All right, that is all we have for today. Hopefully you took good notes. Write down any questions that you have, and come to class prepared tomorrow to ask questions. Thanks a lot.